Okay, this is the 2022 component 1 paper. Okay, so the first question, if you remember what the 2-input NAND gate is, you can get to the 3-input one from there. So always remember the 2-input one. In fact, always remember what an AND gate looks like. I know an AND gate looks like that. That's an AND gate, so I know a NAND is the opposite. Okay, so basically any time I'm going to get a 0 is when everything is a 1, so a 0 there. Yeah. Okay. Right, now it says about drawing it, so you should be really comfortable with doing that. Remember, an AND gate is a NAND with a NOT on the end, dead easy. You can draw a NOT gate using a NAND quite easily. The OR gate is one that uses 3 NAND gates. And then remember, 2 NOTs in a row cancel. So let me reveal the answers for that one there. So you can see over here you've got some cancellations that could actually happen. Okay, so you've got this one would cancel with this, and then this one would cancel with this. Make sure you do the lines the other way. Okay, so that would be your maximum marks for that first question. Okay, referring to the circuits on the previous page, explain the benefits of using NAND gate circuit equivalent. Well, obviously it's the idea that fewer chips would be needed. So if you looked at the previous question, you would see that one chip, we call them ICs, integrated circuits. So one IC would be needed with the NAND gates. And you can see that 3 ICs would be needed for not converting to NAND. So please write that down. I'll put the mark scheme up in a moment. But let's go over this next one. Again, straightforward. Remember how these work. These NAND gate, well, SR flip-flops essentially. Remember, Q changes when S goes low or R goes low. So the first bit's been done for you. The next one, look, notice R has gone low. R has gone low there. So Q should change. So Q should be reset. Okay. Nothing happens on that third one down because R or S hasn't changed. This next one, S has gone low, so we set because S has gone low. Nothing happens on the next one. The last one, S and R both go low. That's the unused state. That's when Q and not Q would both become logic 1s, which doesn't make any sense, does it? So you can't set and reset at the same time. In fact, the next bit, state one problem with the circuit above. The idea is that Q and not Q are both logic 1s, which is kind of an undesirable state. It's an unused state. You wouldn't use it in that state. Okay, so as you can see on the mark scheme, it says a disallowed state. Okay, the last bit, give a practical application of the circuit above. The obvious one is an alarm or memory. I would give switch bounce as an answer as well. I'm pretty sure the examiner would give that, but just write, you know, if you know more than one, just write them down. Alarm, memory, switch bounce. You know that the SR flip-flops do all of those things. But I suppose the first thing to come to mind would actually be memory. You can see on that first one there, fewer chips needed, ICs. You could write microchips. You'll be fine with that. Okay. Okay. Anything ANDed with 1 is itself A, and 1 is just A. Okay. B ANDed with not B. That's essentially 1 and 0. What would that always equal? Okay, yeah. Obviously, you're not going to get anything out there. Right, I'm going to do this one with you. So first one, split the line, change the size. So let's just write it out here. So we're going to have A and B and not C with 2 lines above it. This, obviously the sign I'm changing is that one there, so it's going to an and I'm going to have A and B with 1 line above it. Okay, so that's stage 1. Stage 2, your doubles cancel, double lines cancel, so let's go for the next stage. So we're going to have A and B and not C, and with open up the bracket, it's going to be not A or B. Okay. That's 2 of the 4 marks. Third mark is to realise, well, I've got a bracket, I've got something got A and B and not C and a bracket. So I can move these around any way I see fit. I'm going to move the B over towards the bracket because I can see a B inside the bracket, and you'll see why. So I'm going to rewrite this as A and not C and B, ended with open my bracket, not A or B. Right, okay, let's just do a super big bracket around there. Okay, this is a Boolean identity. It's on the data sheet. If you want me to go over it with you, I can do in lesson, but it's the one where it gets, not A gets absorbed. That just equals B. Okay, just have to take my word for it. It just equals B. Come and see me if you want me to actually go through the maths behind that. Okay, but I think most of you might be able to spot that anyway, but it is on the data sheet as well. So it's quite simply A and not C and B. There's your final answer. It's 4 marks. 4 marks for that. And the next one is grouping. Remember, the larger the group, the better. I can see, well, you tell me, how many groups can you see there? Yes, hopefully you've seen 2 groups of 4 and 1 group of 2, if done correctly. I'm just going to put the mark scheme up now. Okay, so yeah, 2 groups of 4 and 1 group of 2. There are your answers there. Okay, don't forget you can't cancel anything from there. Okay, you can you know, you can factorize, but don't worry about that. Just leave it as that. That's your answer. Okay, so straightforward there. You've got 1, 2, 6, 7, 8, 9 relatively easy marks for easy stuff. Okay, another 6 easy marks. Basically, as long as you know your logic gates. If you don't know your logic gates by now, then you really need to, because you know we're in the second year. We're nearly 2 years into the course now. There's only 7 things. Right. So L is the not of B. M is the NAND of A and L. So A NAND L. N is the OR, but L and C are the inputs, and then you've got an X NOR at the end. Okay, I'm not going to just do that. I'll just show the answer. It'll be a bit easier. So just have a little look at that. Just take your time. But it is straightforward, isn't it? If you're unsure, then you might need to come and see me. But there's the mark scheme for that. Hopefully me explaining it has helped. And then literally just write the Boolean expression without simplifying. So where Q is, you've got 4 ones where Q is. So it's going to be 4 expressions, something or something or something or something else. Right, let's have a read of this one. To avoid damage, a wind turbine has a maximum speed of 20 revs per minute. A block diagram is shown there. So you guys know how to do a block diagram, or what it looks like. So you've got a slotted disk, you've got the Schmidt inverter, which will obviously digitize it, make it digital, make it nice ones and zeros onto your counter display. Okay, so the encoder uses slotted disk with 50 slots. So that will be 1 whole revolution. You've got 50 slots there. The counting system records 200 pulses in a 30-second period. Calculate the rotational speed in RPM. Now, there's different ways to do this. I'll show you my way, but you can do it differently. I don't really, you know, whichever way you fancy. Let's get my pen out for that one. So, 200 pulses in a 30-second period, and I need revs per minute. So I need to turn that into minutes, 30 into minutes. So I'm going to straight away go 200 times 2, because that's going to put it into minutes, equals 400 pulses per minute. Okay, so that's pulses per minute. Now the encoder, we have 50 slots. Okay, so you've got 50 slots there. So, and it's basically calculating the rotational speed, revs per minute. So it's essentially therefore going to be your 400 pulses per minute divided by the 50 slots equals 8 revs per minute. So 400 pulses per minute will actually be 8 revs per minute because it's 50. The examiner, as you can see on the mark scheme, slightly different, but it doesn't matter as long as that makes sense. Converting Just need to think about what's going on there. Calculate the number of slots that would be counted in 1 minute at the maximum acceptable speed. Well, if the maximum acceptable speed is 20 revs in a minute, how many of those pulses will it be counting? Well, it's counting 400 pulses in a minute. It's doing 20 revolutions. Then obviously we can work between those ones there. Okay, so number of slots. So 20 revs per minute. Oh, sorry, yeah, number of slots. Yes, 50 slots. Sorry about that. 400 pulses. So 50 slots. So you've got 50 slots. 20 revs per minute. Literally multiply the two together to give you the total number of slots. So 20 multiplied by your 50. Oh, 50. Okay, will be 1,000. Hope that makes sense. Right, next one. This is just going to be Ohm's law, I bet. Always is. A lot of this paper is Ohm's law. You know that. So the Schmitt inverter outputs 5 volts for logic 1. The LED has a forward volt drop of 2.1, so 2.1 there. We know there's 20 milliamps going down there. And then we need to work out the resistor value to limit the current. So it's obviously going to be the rest of the voltage there, isn't it? Which is your 2.9 volts. So it's going to be 2.9 volts divided by your 20 milliamps. As you can see up there, it's 145. Okay, 145 ohms. Okay, so a photodiode is used as part of the encoder. Describe what happens in the circuit when light falls on the photodiode. Okay, so straightforward, hopefully. As light falls on the photodiode, current will flow into the base of the transistor. The transistor will switch on, therefore V out should drop to 0 volts. When a transistor is saturated, the voltage across it is 0. Yeah, so obviously all the voltage will be across the that resistor there. So that's the idea of that. So that'll be 3 marks. I'll put the mark scheme up in a moment. State the purpose of the Schmitt inverter. I've said it before. It will obviously ensure that the signal is sharp, because if you've got a slotted disc, it might gradually turn on. So it will almost be like an analogy type signal, won't it? Almost like a noise. You know, we did noise and distortion. Be a bit like that. We want the signal to be sharp, don't we? Or you could say it digitizes the signal, something like that. You can see there are the answers for that one. Okay, you know these always crop up with op amps, don't you? Transfer characteristics, V out against V in, dead easy. What is the maximum input voltage before saturation occurs? Well, it's there, isn't it? I get that as 0.6 volts. To be honest, you could put plus or minus. I think I'd be tempted to put plus or minus, to be honest. And calculate the voltage gain. Choose a suitable value on this gradient, a suitable place. I think there's the most suitable place. Look, 10 volts and 0.5. Yeah. So 10 over your 0.5 is a gain of 20, and it's obviously non-inverting, isn't it? There is a mark for reading values on your graph correctly, so I'd probably dot across on the graph as well. I know it's obvious if you did 10 over 0.5, but just dot across, it can't hurt. And with a gain of 20, draw me a non-inverting op amp. What value will the resistors be? Of course, there'll be a ratio of 1 to 19, because remember the equation is 1 plus RF over R1. Non-inverting, V in goes into the non-inverting input. Resistors still link back to the inverting input, unless it's obviously a Schmitt trigger, which will be in component 2. But there you go, there's your answer, dead easy. So RF would be 19K, R1 would be 1K, for example. 4 marks, lovely. Right, let's see if I can plot this then. Here we go. Right, gain, but I've worked these out, by the way, but I'm doing gain is V out over V in. So all these gains have been been worked out for you. Right, let's have a look. So gain of 41 with 2. Struggling, going to try my best on here. 4 is a gain of 41 as well. 6 is 39. 8 is 28.4. There's 30. There's 28.4. 10 is 19.8. So 10 is about 20-ish. 12 is 12.4. 11, 12, 12.4. And then 14 is 10.4. Something like that. So we're going to go, like that. And we're going to go down there. And we're going to curve off there. Okay. You might want to do a little bit neater because I'm trying to use my whack-on pen. As you can see, it's not the best. But anyway, so yeah, I've just given you a mark scheme on there. All plots correct. Correct shape, smooth line. Okay. Part I will explain on the next page. So just remember how we've plotted that one there. Okay, so this one we had to evaluate. So the amplifier has to have a gain of 40 with a tolerance of plus or minus 2 and a bandwidth of 10k with a tolerance of plus or minus 1k. Use the results to evaluate this against the requirements. So it's 5 marks here. So the first one is to say, well, it's got a gain of 41. So you can read that off the graph. So say it's got a gain of 41. That is within tolerance or plus or minus 2. That'll be 2 marks in total for that. Next one is to do the bandwidth. So remember how you do your bandwidth. Let's just get the pen out again. Obviously, please do this on the previous page, but basically the shape of your graph was something like that, wasn't it? Go 70%, go across and go down. Okay, read off the bandwidth to see if it's in tolerance. I believe the mark scheme says that the correct graph and the bandwidth, you've done that for a mark obviously there. It should be 8k, around 8k. So then you need to say it is outside the specification. So that'll be your 5th mark. Okay, so you get 2 marks for your gain, saying it's within tolerance, 3 marks for your bandwidth, but you need to say it's outside of tolerance or outside of the specification. So that's evaluated it against those requirements, hasn't it? Okay, we've recently done this, dead easy stuff, isn't it? Type of filter, low frequencies can't get through that capacitor, can they? High ones can. So it's a high pass filter, isn't it? A high pass filter. Okay, it's on there. Okay, calculate the breakpoint. That's FB is 1 over 2 pi FC, isn't it? Sorry, 1 over 2 pi RC. Okay, so there's C, there's R. Make sure you got nano and kilo in there. If you do that correctly, you'll get 2.73k. Dead easy, 3 marks. Really easy. Calculate the reactance. Well, we know reactance is XC, isn't it? XC is 1 over 2 pi FC. Yeah. So you're going to be using a different F for this bit and a different F for this bit. Everything else is going to be the same. See what you get. Okay, so I'm just going to use the mark scheme. So it says that you've got 84.7k or 847 ohms. So 84 kilo ohms or 85 kilo ohms or 847 ohms. Okay. Okay, calculate the peak output voltage at the 200 hertz. So it's like a potential divider now, isn't it? Do you remember that one? So we need to use the we need to find the impedance for this one, don't we? Okay. So if you have a look over here, let's see if we can do it, shall we? So let's find the impedance of the circuit first of all. So I'm going to work out Z first. Square root of XC squared plus R squared. Okay, so let's work out the impedance. Do this on the calculator. Guys, you might want to do this as well while I'm doing it. So So XC, which it was for 200 hertz, wasn't it? So 84. Okay, take the square root of that. Square root of answer. Okay, so I get 84926, 85. Around about 85 actually. Okay, so that's what I get there. So we know that V out equals potential divider, so it's going to be R over Z, isn't it, times V in, which is 10 in this case. So if I do this, keep it in my calculator, I should be able to invert that, times it by 6200. Shame you can't see my calculator. Times that by 10 now. Times that by 10. 0.73 I get. Yeah, 0.73, brilliant. Okay, so that's potential divider, but you need to find the Z bit. Okay. Okay, calculate V out at the break frequency. Well, that's dead easy. It's basically 70%, isn't it? So if it's 10 volts going in at the break frequency, it'll be 7 volts coming out. Okay, so 7 volts coming out. Okay, and then obviously sketch the graph. Now it doesn't tell you whether it needs to be logarithmic or linear, does it? It's a bit of a funny one there. I think if it doesn't tell me, I would have been tempted to have gone this one personally, a linear type one, where it kind of does that, and you go 70%, which is 7 volts, go across, and then write down your break frequency, which was what, 2.73 was it? 2.73. That's what I would have been tempted to do, going up to 10 volts. You can actually do it as a log scale if you want, though. Look, log scale there. So, okay. Okay. Design a flash converter to meet the following spec. Include all relevant values. The input voltage range is 4 volts, which therefore should mean the reference will be 4 volts. 2-bit binary output. It's got an overflow there, as you can see. So you're going to need your 4 resistors. You're going to need 4 op amps. If it doesn't have the overflow, just be 3 op amps. Okay. I'm just going to show you the answer rather than me sketching it. There you go. So you can see you've got the 4 volts there. You've got the 4 volts there. You've got the 4 resistors, and you're going into B in there. Okay, so that's 5 marks. You're not even calculating any values there. So 5 easy marks for that one. Okay, good old transistors. Dead easy, isn't it, transistors? So we've got a cafe owner was an automated system to control windows in a cafe. So they want the windows to be opened by a solenoid when the temperature is too high. Okay. So first of all, add a component to the diagram to protect the transistor during switching. Remember what component we always use to protect the transistor. It's the diode, isn't it? So you put a diode that's called back EMF. Okay, put that there, back EMF. Okay, that's dead easy, isn't it? Okay, so when the transistor is saturated, V1 equals 6.4 volts. Okay, what voltage is always there when a transistor is just saturated? I think you all know this now. Don't know how many times we've done that, probably about 70 times. Okay, so we know that voltage there, we know that voltage there. So what voltage is going to be across here? Oh, what voltage is going to be across there? Therefore, it's going to be the remainder, which is 5.7, isn't it? 5.7 volts. Yeah, because you know you've got 6.4 to start with. You lose your 5.7, you lose your 0.7. They should add up. Okay, so work out your base current. Well, where are we? Oh, we have to work out the base current from finding the collector current and then dividing it by 120. So we can work out the collector current dead easy. So I'm going to work out collector current, IC. If by doing 9 volts divided by 15. It's Ohm's law, isn't it? I equals V over R, so 9 divided by 15. Winding down my head, 0.6 amps. 0.6 amps. I'll write it in milliamps. Okay, I know that the input current is therefore now going to be 120th. Just think logically. Is the input current going to be higher or lower? If the amplification of this system is 120, the current going in is 120th. So that's in milliamps. Okay. Now the next bit, the ideal value for RB, and select a suitable value from the E24 series. Okay. So the theoretical value for RB would be R equals V over I, obviously, doesn't it? Where it's going to be V over IB, isn't it? Of course it is. So it's going to be your 5.7 over your 5 milliamps. This will come out in kilo ohms. 7 divided by 5, 1.14. Right, on your data sheet you've got the E24 series. Now you need to think to yourself, would you go for a higher resistor value or a lower one? Well, if you went for a higher resistor value, there would be a little bit less current, which wouldn't be enough to saturate the transistor. We need to go for the lower resistor value, because then there'll be enough to saturate the transistor. It doesn't actually matter if I've got a little bit more current than needed, but we need to go for the lower value from the E24 series. Okay, so you've got the 1.1 kilo ohm resistor that you could choose from there. Okay, nice. Okay, so we need to plot V out against V in. Okay, so just get my pen again, sorry. V out is VCE, by the way, is that bit there. VCE is the same. So we know when a transistor is off, all the voltages across it, 9 volts. When you get to about 0.7 volts, it will start to turn on. And then it will be fully on when V1 reaches, was it 6.4, wasn't it? About 6.4-ish, so about there-ish, I think it will be. There's 7, yeah, about there will be fully on. So it's going to be kind of like, better drawing than me, please. Off, active, saturated. Remember, the gradient's the active bit, the off bit is there, and the saturated bit is there. Okay. It's okay, actually, yeah, thank you. Oh, no, it's fine. Sorry about that, it's Keena just coming in there. I'm at work doing this. Right. So, where are we? So once we've done that, find the V1. Temperature drops and V1 changes to 4.5. So use your graph to find VCE. So 4.5 volts is about there-ish. Go across, and then we should find VCE. And then calculate the collector current at this value and the power dissipated in the transistor. So I'll put the mark scheme on, and then we'll talk about how to do this. So we have got 3 volts there. So I'm going to label this on this transistor over here now. So I'm going to put 3 volts at that point. So what voltage will be at that point there? Obviously 6 volts will be there, won't it? If there's 6 volts there and it's 15 ohms, I can work out the new collector current. So IC is 6 volts divided by 15. .4 amps. And then work out the power dissipated in the transistor. power is V times I, so dead easy, power is V times I. The voltage is the 3 volts, and the I bit is the 0.4. 1.2 watts. That's 5 marks. Really easy stuff, isn't it? It's just Ohm's law, series circuit rules. Don't be scared by transistors. They're not difficult. They're circuit rules, Ohm's law, series circuit rules. Power is V times I. There's really nothing more to them. Right, okay, so we have wireless comms. This is an AM wave. Why is it an AM wave? Because the A is being M'd. The amplitude is being modulated. Okay, determine the period of the audio signal and calculate its frequency. So time period of the audio is the, let's get my pen. It's this bit here, this bit, this is the audio, this bit here, like that. So take one peak, let's take from there to the next peak, let's take to there. How long is that? Can I do that in my head? I think I can. That looks like 160. So the time period equals 160 microseconds, and then obviously the frequency is 1 over 160 times 10 to the minus 6. 6250. Okay, I don't know why you get 3 marks for that, but maybe you might have to show it on here. You can see, guys, there's a lot of marks for quite simple stuff. Yeah, dead easy, isn't it, really? Anyway, the depth of modulation. Now, there is an equation on the data sheet which you can use, Vmax plus Vmin over Vmax minus Vmin. I'm more than happy for you guys to do that, but do you remember I always did the B over A one? But it just depends on what you prefer. So if you did do the B over A one, I know it's going between 0.5 and 1.5, so I know that 1 is the middle bit, because that's half. But, you know, if it's going between 0.5 and 1.5, halfway between that bit becomes my A, then the B bit becomes that. So if I did it that way, it would be B over A times 100, B 0.5 over 1 times 100, which you can do, that's fine. Or you can use the equation on a data sheet, which you get the same answer. Okay, so 50% there. So it's entirely up to you. Okay. Okay, good old frequency spectrums. The frequency spectrum means lines. Frequency response will be a curve. The carrier frequency is the one in the middle. That's obviously 585 kilohertz. The broadcast bandwidth is from the left position to the right position. So the broadcast bandwidth, let's get my pen. Broadcast bandwidth is there to there. Okay, that's the broadcast bandwidth. Okay, so 77, 87, so that's 15, isn't it? 16, sorry, 16, yeah. So broadcast bandwidth would be 16K. Okay. You do get base bandwidth, just so you know. If it says base bandwidth ever, it's just from there to there, so it'll be 8K. Base bandwidth would equal 8 kilohertz, because it's from the base position, which makes obvious sense, doesn't it? Broadcast is the whole thing. Explain what is meant by frequency division multiplexing. It's a way of getting more than one frequency on the same sort of channel or channel. So I'll put the mark scheme on in a moment so you can look at that. And then basically you need to work out how many of these channels will fit, how many of these signals will fit in that range. So let me show you the mark scheme for those. So yeah, part C, several independent units can send signals at once. Each signal is assigned a frequency and a range. You can accept a graphical answer. So some of you might like to do it as a graphic and actually put the stations next to each other like that. Yeah, because remember we've done that as well as example, so you might want to do that and explain it as well. And then obviously the number of stations is going to be the total broadcast band, which is 1605 minus 5305, and then divided by your broadcast bandwidth. So 66.88, therefore 66 stations slap bang next to each other would fit. I hope that makes sense. Okay for you guys. Okay, I'll give you the mark scheme for this one, just because they're better explaining things than I am. So it says FM is an alternative modulation technique, as we know. Describe how an audio signal changes in the carrier. So it's basically the voltage of the signal, of the audio signal, is modulating or changing the frequency. So the voltage of the audio signal is changing the frequency. The frequency of the audio signal is modulated as the rate of change of the frequency in the carrier wave. So if basically what we're trying to say is if the audio signal was 20 kilohertz, it would oscillate 20,000. The carrier would be oscillating 20,000 times per second. Remember, we've done a question on that. The advantage of FM over AM is it's less susceptible to noise. So no information is carried in the amplitude, so therefore it will be less susceptible. These next two are dead easy. I can't believe they give you 4 marks for it. 8 megahertz carrier, that's got nothing to do with the question. You've got 10 kilohertz, 40 kilohertz deviation. It says it in the question. FI, F with a little triangle, that's deviation, isn't it? So you can work that one out. And the bandwidth is given in the question, so it's quite easy. Okay, let's build a comparator, shall we? So we've got a buzzer, light level drops below. Okay, so we'll do that in a minute. Increases to 4 volts. Okay, so 4 volts is a switching voltage as well. So all we do is we're going to have, sorry, the answer's come up there, but it doesn't matter, let's still do it. So all we're going to do is we're going to have resistor, like that, another one up there, like that. Right, so it comes on when the light level drops. So as light goes down, resistance goes up, which means obviously the voltage would be increasing. So if that voltage is increasing, this is going to go to the plus sign, isn't it? That's going to go to there. That's going to go to there. Okay. And then obviously it switches at 4 volts. Well, why don't we make that 4K? 8 volts, make it 8K. Simple as that, really. Don't need a calculator. Just make it as easy as possible. Oh no, these look scary. They're not too scary, they're okay. MOSFETs. There's only 2 equations that they can give you for MOSFETs. Think of it like, you know, the gain of it, or yeah, gain equals V out over V in. You can look at it like that. Let's write it like that if you want. So gain, let's get my pen. Gain, which in this case is transconductance. Let's write it like I just said. Gain equals V out. In this case, it's the output. Well, I know the output is the ID, the drain current, over the input, which is a VGS minus 3. So that's the equation. It's on the data sheet anyway. Okay, what are we going to use for ID? We're going to use the 5 amps. So we're going to use the 5 amps there. And then the op amp saturates at 11 volts, so there we go. So we've got 11 volts there. So 11 minus 3. Can't believe how easy this is with 3 marks. 5 divided by 8. 5 divided by 8. So 0.625. 0.625. Capital S for Siemens. Calculate the power dissipated in the MOSFET. There's even an equation on the data sheet for that. Power equals, well, it's I squared R, but in this case it's the drain current squared multiplied by resistance between the drain and the source when it's on. It's on the data sheet, but I is 5 squared multiplied by 0.2, 25, which is 5 watts. Yeah. So don't be scared by MOSFETs. There's nothing to them. Okay, this one I'll use my laser pointer. Right. A voltage amplifier meets the following, which meets the following spec is there. So gain of -50, input impedance of 12, bandwidth of 15, and an undistorted output for signals and amplitude of that. This is a student's design. They've designed that. Okay. Evaluate the circuit against a spec supported with relevant calculations and describe any changes that you would make. Well, where's the first spec? It says a gain of -50. Is that the case first of all? So work out your gain. I know that -50, that is okay. So you go 500 divided by 10 equals -50. Yes, that's fine. Input impedance of 12k. That is incorrect. So make sure you say that the input impedance is incorrect. It is 10k. A bandwidth of at least 15k. You can work out your bandwidth because you know your gain bandwidth product and you know your gain. Okay, so bandwidth calculated. So it says that this does meet, or in fact it exceeds the third parameter. So it does say at least 15k. So that's okay. Your last one, an undistorted output for this input signals with an amplitude of 250 millivolts. So if you put 250 millivolts going in, it says that the amplitude, the op-amp will saturate at 200 millivolts. Any voltage above that will be distorted, so it does not meet the fourth parameter. Okay, so we've got that one because it saturates at 10. So you'll find that it does not meet that fourth parameter. So changes. So you've mentioned all of that. Changes to be made. Maybe change your input resistance to 12k, which would obviously make sense, which would obviously mean that RF would have to change to 600k. You'll need to mention that to maintain that gain. And then change the power supply. So if you made the power supply at least 12.5, then that would remain undistorted. They are the two changes you can make. It's quality for extended response. So if you've got all of this and it's very coherent, you'll get 6 marks. If you've got some of it, 3 or 4 marks. If you really don't understand what you're doing, you're going to get 0, 1 or 2 marks. Okay, but I hope that makes sense. I haven't mentioned a lot about QER questions, but every paper will have one, quality of extended response. So it will ask you about an experiment, or it might give you, like you say, this, where there's something wrong, and then you have to try and work through it. But again, it's all stuff that you've done, so just take your time, think about what it's asking, and work your way through it. Okay, so we need to find slew rate here. Okay, so we have, first of all, slew rate. Oh, I've given you the answer there, but that's fine. Let's just put it on here anyway. So slew rate is V out over time. We need to find time. So that would be V out over slew rate. Okay. So be a 10 over your 0.5, which would be 20 microseconds. And then you quite simply plot it because it's inverting. Your 10, by the way, is a maximum V out before it saturates, isn't it? But if it's changing at a rate of 0.5 volts for every 1 microsecond, I know that 10 microseconds it would have changed 5 volts, wouldn't it? So minus 5 volts for 10 microseconds. So that would be your first data point. Continue that down till it saturates, which is minus 10 volts, and go across. Okay. This last bit, it says we now change to a peak voltage of 200 millivolts. Now we need to work out the frequency. So you can work out slew rate by using this equation here. Okay. In fact, we've been given slew rate, so we need to work out the frequency. So you rearrange that equation to make f the subject. Okay, so obviously f would equal, divide everything by 2 pi v essentially, so it'll be slew rate divided by 2 pi vp. That's your rearrangement. The slew rate is, don't forget, we need to convert microseconds, 0.5 volts for every 1 microsecond. So we times that by 1,000,000. Yeah, so it's actually 0.5 times 10 to the 6 divided by 2 pi, and then don't forget the peak voltage. I've been given the input voltage. So to get the peak voltage, we times it by the gain, don't we? V in times gain. That's where that 50 comes from. So that's the peak voltage is the input times the gain. So make sure you do that as well. Don't just put the 200 in for that one. Okay. Okay, we've done this one quite a few times, so I'm not going to draw it out, but I'll just show you the answers. Obviously, attenuation, the amplitude reduces, doesn't it, as it travels through the wire. Probably worth mentioning the frequency is unchanged, okay, as well. Okay, next one, we've been given the length, we've been given the power loss. We know that there's 2 amplifiers with gains of 10 been placed along there, so we need to work out the input power to give an output power of 5 nanowatts. Okay, so hopefully you can look at the mark scheme on all of that one there. So I'll leave the mark scheme on so you can have a look. And the last one is the signal to noise ratio equation, which again we've looked at quite a lot of these as we've gone through. So have a look at this one here. Okay, if you think that you need a little bit more work on this one, then obviously pop in and see us for a support session for your next assessment. Okay.